Hello students, this is Mr. Ezra. This is our last video for Unit 4C. We've been talking about how to graph rational functions. There were lots of things that we had to do before we actually got to the graphs. We've got to the graphs, and now we want to talk about characteristics of these functions. So let's get started. So there are several characteristics of functions that we have talked about in previous units. So we've already talked about how to find intervals of increase and decrease. We've already talked about maximums and minimums, and we've already talked about domain and range. So what we're really kind of doing is talking about those things in the context of this type of function. And since each of them is kind of unique in the look and the feel, we're going to look at several examples today, and hopefully by the end of this you'll feel good about these characteristics. I want to point out before we begin that in this video and in this lesson, when we talk about maximums and minimums, we're talking about what we call a local max or min or a relative max or min. In other words, there is a difference between a local minimum and an absolute minimum, right? Remember, absolute minimums and absolute maximums are the highest or the lowest points on the graph, period. Well, these functions tend to always have an arrow up and always have an arrow down. So we're not going to be talking about absolutes, but instead relatives. And remember, those relative minimums are, the function has to be increasing and change directions to be a local maximum, or it has to be decreasing and change directions to have a local minimum. So that's, number one, we're only talking about the local minimums and maximums. We'll find with the domain, range, intervals of increase and decrease that this is very similar to things that we've done before. So let's go ahead and begin. We'll start with example one. We've already graphed all the asymptotes and the holes and the intercepts, and now we want to describe the characteristics. So remember, with intervals of increase and decrease, we only use x values to describe that. So we want to know, where is the function increasing from left to right? Where is it decreasing from left to right? So the first thing we want to look at is what's happening on the graph. We notice that on the very far left, which would be considered negative infinity, our function is very slowly going downhill, and eventually it picks up speed and it goes downhill very fast up into the asymptote. So that means we have a decreasing interval from negative infinity to the asymptote, which is at positive an x value of +2. So we've got the interval of decrease from negative infinity to +2. Then there's a little bit of an asymptote. No function exists there. And then we, again, are going downhill on the right side of the asymptote. So we're going to union this with the right side of 2 to positive infinity. So we're essentially decreasing forever along this graph. Everywhere there's a function, we're decreasing, but there's no function at x equals 2, so we have to kind of cut it off there and start it up at there again. And remember, those parentheses mean that we're not including 2. Since this function is always decreasing, there would be no interval of increase. Now, we're talking about maxes and mins that are local or relative, and that means that the function has to be increasing and change direction, decreasing or decreasing and changing directions to increasing. That doesn't happen in this function. There is no maximum and there is no minimum in this example. Now, when we think about the domain and the range, what I want you to think about are the exclusions in the domain and range. So we have in the past used interval notation to describe this. Today, I'm going to do it a little differently. I'm going to say that our domain is all real numbers of x except where the domain does not exist. And it does not exist at an x value of 2. So we're going to say all real numbers except +2. That's a way to say everything from negative infinity to positive infinity, but not 2. Now, if you wanted to use interval notation, it would look exactly like what we put for the interval of decrease, because our domain exists from negative infinity to the asymptote, does not exist there, so we'd have to in the parentheses, and then we'd have to start again on the right and say that we have x values forever to the right. So we could write it in interval notation, and that would be fine. I just want to kind of give it its own flavor for this unit. For the range, we're talking about y values. So when we go bottom to top, where there is a horizontal asymptote that is not crossed, we're going to have another limit on the, we're going to have a limit on the range. So this is going to be all real numbers for the range, except there is a y value that does not exist on the function, and that is a y value of positive 3. So we're going to say all real numbers, that symbol R with the 2 lines is all real numbers, except positive 3. So what I'm really listing out here are the limits on the domain, the places where the domain does not exist, and the limits on the range, the places where the range does not exist. In example 2, intervals of increase or decrease, we'll start on the left. We notice that it is going uphill, right? So that's increasing to the asymptote, and the asymptote is at -2. I then notice that it is increasing to right here, this one spot. So it's increasing from -2 to this x value of 0. And then it decreases, right? It changes direction. So it starts decreasing to the asymptote of +2. And then on the right side of that, it's decreasing forever. So it looks like we're going to have 2 intervals of increase and 2 intervals of decrease. 2 intervals of increase and then 2 intervals of decrease. So intervals of increase are going to be from -infinity to the asymptote of -2, union, -2 to 0. Everything gets parentheses, right? Intervals of increase and decrease always get parentheses. The decrease, we're going to start at 0 to the asymptote of 2. We're going to union that from 2 to infinity. Now, maxes and mins they do happen, and in this case it does. There's a local maximum where this function is increasing, and about right here it stops increasing and starts to decrease. So we need to mention that point. It looks like it is a y-intercept, which was at 0, -1/2. So that maximum value, that local maximum, is going to be 0, -1/2. There is a way in your graphing calculator to find these. If you want me to show you in class, just ask me and I'll review with you how to find maximums in your graphing calculator. There is no minimum here because there's no place where the function is decreasing and it changes direction. It's going up forever on this part of the function. It's going down forever on this part. It's only got the maximum right here. So we have no minimum. Domain is limited here. So remember, we've got all real numbers except, and where does the function not exist? Well, it doesn't exist at -2. It doesn't exist at +2 because those are asymptotes. The range is also all real numbers, all y values, except for the one horizontal asymptote at 0. So I want you to think of, for the domain, look for vertical asymptotes and holes if there are any. Those are going to be limits on the domain. And for the range, look for horizontal asymptotes and holes if there are any, and those will be limits on the range. Example 3, let's see if we can start picking up some speed here. So we are decreasing to the asymptote of -2. Again, we are decreasing to this y-intercept right here, it looks like, which is at a x value of 0. Remember, we only use x values for these intervals. We increase to the right asymptote of +2, and then we're increasing again. So intervals of increase, we're starting at 0 to 2, and we're unioning that with 2 to +infinity. The intervals of decrease, remember, go left to right with this, right? Left from -infinity to -2. Union -2 to 0. All right, is there a local maximum? Well, no, there's no kind of highest mountaintoppy kind of a point, but there is a minimum. There is a place where it changes direction at a little valley, and this happens to be, again, the y-intercept. So that point would be 0, 3 3/4. Okay, domain is going to be all real numbers except the places where there are vertical asymptote, so that's -2 and +2. The range is going to be all real numbers except the place where there is a horizontal asymptote, which is at +1. Example 4. All right, so let's look at intervals of increase. I like to kind of mark the top of this. We're increasing. And we don't see it, but it keeps going up towards the asymptote there, and that has an x value of -2. So I'm going to put a little -2 there. And then I'm also increasing on the right side forever to the right. So I'm increasing from -infinity to -2. And I'm increasing from -2 to +infinity. There's no interval of decrease. It never goes down. There's no local max or no local minimum. And the domain and range are all real numbers for the domain except for where we have that asymptote, that vertical asymptote at -2. And for the range, it's all real numbers except where we have the horizontal asymptote on the y-axis, which is at +5. Example 5. Let's see, intervals of increase. So we're increasing to the asymptote of -2, increasing to 0, decreasing to the asymptote of +2, and then decreasing again. All right, so let's get this down. Increasing from -infinity to -2 union, -2 to 0 again, and decreasing from 0. I like to go left to right with these. I recommend that you do that too. 0 to 2. Asymptotes break things up, don't they? And then 2 to infinity. There is a local maximum right here that it is in these examples kind of working out to be a y-intercept. That is not always the case. So don't think that that's always the case, but we tend to have that happening here. So that's going to be at a maximum at 0, -2.5. There is no local minimum. Right, domain, all real numbers except where the function does not exist for x values, which would be the vertical asymptote of -2 and +2. The range is all real numbers except for where there is a horizontal asymptote. In this case, that is at 0. Example 6, decreasing to the asymptote of -3. Then we are still decreasing forever. So we're going downhill forever except where there's the asymptote. So no interval of increase. We're decreasing from -infinity to -3 union -3 to infinity. There is no local max and no local min. The domain is going to be all real numbers except for -3. That is the x value limitation. And the range is going to be all real numbers except 0, which is the limit on y, or on the y values. All right, now we did have some extra examples, and these include something called a hole, and I want to make sure that we talk about this because holes also limit the domain and range, and they also can limit intervals of increase and decrease. We're decreasing through this hole, but we're not decreasing at the hole. We're going to decrease until we get to the hole, which is an x value of -2. Then we're going to decrease till we get to the asymptote, which is at +3. And then we're going to decrease again. So we're always decreasing, but because we write these intervals in interval notation, we're going to have to talk about where it's decreasing. So we start at -infinity, you go left to right. We stop decreasing for just a second at the hole, the x value of the hole. Then we're decreasing again from the hole to the asymptote. And then we're decreasing again from the asymptote forever to the right. So we're really saying we're decreasing everywhere except where we don't have x values. You know, we can't decrease if there's not an x value there. In this function, we never increase. It's never going uphill. There are no local maxes and no local mins. There's no turning points where we change directions. All right, so limits on the domain. All real numbers except any x value of a whole is a limitation on the domain. So this whole has an x value of -2. That's a limit on the domain. Any vertical asymptote, limit on the domain. So not at -2 and not at +3. Those are the two places that x does not exist. The same thing is true for the range. It's all real numbers because we've got these arrows down and up, except there's a few places where the range does not exist, where there's a limit on the domain. That would be where the y value of the whole, which was 1/5. And it would be the y value of the asymptote, which was +1. So all y values are possible except 1/5 and +1 in this example. All right, our last extra example here, we have interval of increase. It looks like this function is increasing forever except where the whole is, right? So we're increasing from -infinity to the x value of the whole, which is 5, and then we start increasing again. So interval of increase would be from -infinity to the whole, x value of 5, and union that with everything to the right of the whole. There is no interval of decrease. There is no maximum, no local minimum. Domain, all real numbers except wholes limit the domain. So there is not an x value at 5 on this function because there's a whole there. For the range, the whole limits the range. There's not a y value at 8 here. So we will put all real numbers except for 8. All right, now there are tons of other, I mean, these functions come in lots of varieties, and we don't have any examples with slant asymptotes, and they kind of behave strangely because there's a slanted asymptote and this kind of other asymptote, and we end up with kind of interesting things happen. We're going to have to talk about those in class if you have questions. We might have another little mini lesson on this in class because these are all so unique. But I hope that you get the picture that this is not anything new. You've practiced this before, and I think that you will be successful with it this time as well. Remember, if you run into any questions, feel free to stop me, and I'll see you in class.